use these functions. Well, that's the short answer anyways. The rest of this video will be a project-based approach to taking scientific data and plotting it in Python. First, we'll build a little circuit, then record some voltage, and then import the data into Python and plot it. All the sections in this video will be labeled on the time bar, so feel free to skip through any of my waffling. The data from the oscilloscope and the code for this video will be in the description below. First, let's briefly go over the operation of the circuit so we can better understand the data we'll be taking. A Schmidt trigger is what's called a hysteresis device, and we'll be using it here to create a simple oscillating electrical signal. The working principle is actually pretty straightforward. When the voltage across the capacitor falls low enough, the Schmidt trigger will start outputting the rail voltage, 5 volts in our case. This will begin to charge the capacitor. When the capacitor reaches a high enough voltage, the Schmidt trigger will shut off and the capacitor will begin to discharge. This process creates a cycle which shows up as a square wave at the Schmidt trigger's output and a sawtooth wave across the capacitor. The frequency of this oscillation is inversely proportional to the circuit's capacitance and resistance, and in future video, we'll actually use Python to calculate the frequency of oscillation and see how it's affected by the components we select. But for now, let's get the circuit set up and take some data. Alright, so here we have the circuit all set up. We've got our ground right here and our plus 5 volts right here. We're operating this chip at 5 volts and it is actually a hex inverting Schmidt trigger. So we've gone ahead and grounded all the channels we're not going to be using. And then on channel A, we'll be setting up our circuit right here. Just like the diagram, we have one resistor and one capacitor. This blue line is going to be showing us the output from the Schmidt trigger. And then this orange line is going to be showing us the actual charge on the capacitor. So we can switch over here and we'll be able to see we're not getting anything right now. That's good. Our rails aren't on. As soon as we turn the rails on, we can see that we're getting some oscillation. It's kind of hard to see at this resolution. So we can go ahead and zoom in here. And it should show that we're getting this very clean square wave. That's the output from the Schmidt trigger. And then this sort of sawtooth looking wave. If we zoom in more, we can kind of see that behavior that we were seeing in the diagram. And this is actually the charge on the capacitor. There we go. That looks a lot cleaner. And so basically all this is doing is every time we're hitting a rising edge right here, it's triggering the oscilloscope to take a new data set. So now all we have to do is record this data and we'll be able to bring it into Python and work with it. Alright, so let's go ahead and get started coding. So in this folder we have our data as well as our Python script that we're going to be running. And I've already gone ahead and pulled it up in Sublime and we can see this is what our data looks like. It's a pretty standard output for any kind of program that outputs CSV files. One of the complications is that we're going to have this header right here, but we should be able to get around that pretty easily with the Numpy and the Pandas commands. So let's go ahead and get started. First of all, we're going to need to go ahead and import all of our modules that we're going to be using. For us, we'll be using Matplotlib, and then we'll also be using Numpy, and finally Pandas. So an important thing to note is that these are just aliases. They can be whatever you want, but generally speaking, there's kind of a community accepted alias for these. So if you go and you see other people's code on GitHub and stuff, there's a good chance they'll be using these same aliases. So it's a good habit to just get into using those aliases for these specific modules. So first things first, let's go ahead and create a variable to hold the file name. In our case, it's going to be data.csv. Now there is one important thing to think about when you're specifying the file name. If we don't give it a path, for example, some big path starting from our C drive and going down to the folder, it's going to assume that the folder we're looking for, the file we're looking for, is in the folder that we're running the script from. So this right here is no problem because we know that our script is right here. So it's going to search in this same file. If for some reason the file we're looking for is not in the same folder as the script, we'll have to specify the entire path to that file. So that's not too hard. You can do it like this. And when you do it like that, you'll see that it's going to give us this kind of weird error. When we try to run it, it's going to give us this weird error. That's because these backslashes are currently being interpreted as escape characters. So there's two ways to get around that. One, you can backslash out of the backslash, and that should run. Or the easier way to do it is to just turn it into a raw string, and that's going to allow us to interpret that as just a backslash normal string backslash, and then when we go and print that file name, it's going to show us exactly what we put in. Again, in our case, because the data file is in the same folder as the script we're running, it's really not that important, so we're just going to go ahead and use this data.csv for now. For the sake of completeness, I'll go ahead and show you what it looks like to take in this data as a float value. The reason I'm not going to go too much in depth into this is because there's really not too many situations where you would be wanting to use stock Python over something like Pandas or Numpy. It's going to be a lot slower, and it's going to require, as you can see, a lot more code. It doesn't have to be in like multi-nested list comprehensions like this, but it'll still be quite a bit of code compared to what we're going to do next. But if we go ahead and print this, we can see that it is taking all of that data in. But we'll also be able to do this much more efficiently and much easier. So I'm going to go ahead and show you now how we can do it in Pandas. So as far as reading data in with Pandas, we're just going to be using the pd.read_csv function, and that's going to allow us to just simply supply the file name and read in that data. There will be a couple of things that we need to address first though. For example, if I were to run this right now, it might give me some errors. And this is primarily because 1, we haven't told it the delimiter, and 2, we still have that header that we need to get around here. So this is our header, and we can see that our data doesn't actually start until around line 15. So we'll simply have to specify that as a keyword argument in our function call. For example, skip rows equals 14 in this case because we're looking to keep this header data. And then as far as the delimiter, we can see that it's a comma. So we'll just specify that. And that should allow us to pull in this data. And if we go ahead and print it, we can see that we have our data and it's coming in with the index column, that's that 0 to 8191 that you're seeing there, as well as the labels. So we're going to be importing data 2 ways today, one through Pandas and one through Numpy. While both of them are very similar, they are going to differ in the data structures that they return. This data structure is what's called a data frame, and there's multiple ways to index a data frame. The way we'll be doing it today is by actually specifically referencing the column header that we have defined here. So simply type in the column header of the column that you're trying to get. So now we can see we're getting that one-dimensional array that corresponds to all of the time vector. And if we go ahead and print one of our other columns, we can see that we also have those voltages. So now all we have to do is pass these 2 vectors into our plt.plot function to generate a plot. So let's go ahead and do that. Alright, so we've got it plotted, and we'll just make sure we show that plot, and boom, we're done. So this is pretty much the simplest plot we can generate, so let's go ahead and add some more information, as well as that other waveform. So for the other waveform, we'll simply have to copy this, and go ahead and add the second channel to the same plot. Now we can see that we have that square wave, as well as that sawtooth wave. We can specify labels in the plot by passing in the keyword argument label, as well as the specific label that we're trying to assign to that waveform. For example, channel 1 we know is the sawtooth wave, which is the voltage across the capacitor. So let's go ahead and say capacitor voltage. Channel 2 is the output of the Schmidt trigger. And before it will show up in our plot, we'll have to call the plt.legend function to make sure that it shows up. But now we can see that we actually have the labels associated with each of the waveforms in our plot. Now let's add some axis titles as well as rebase the time. To rebase the time, we simply have to multiply the time vector that we're passing into the plot function by whatever factor we're trying to scale it by. In this case, we'll try to get it into milliseconds, so we'll pass in 1000. Now we can see that we're getting -10 to 10. Now let's go ahead and add our axis titles in. Now we have our axis titles, and let's give our entire plot a title with just the plt.title. And now we have a full plot with our waveforms labeled, rebased to milliseconds for clarity, and our axis titles. So now let's try the same thing in Numpy. We'll start by disabling this code block and moving on to the Numpy section. So for the Numpy section, we'll be using a very similar command called numpy.loadText. We'll simply pass in our file name, and we can use the function in much the same way as we used the previous one. We'll still get errors as we haven't specified our delimiter or the number of rows that we'd like to skip. So let's go ahead and do that right now. So we can type in our delimiter, and then we'll type in the number of rows that we'd like to skip. So we skipped 14 when we were doing our pandas, but if we are to go ahead and do that now, we'll see that it doesn't work. And there's a reason for that. Recall that these two functions are actually giving us two different data types as outputs. So the first function was what's called a data frame. A data frame can support multiple types of data within its structure, whereas a NumPy array can only support one single data type. This becomes a problem when we try to import the headers. So we'll either have to import them separately or forget them altogether. This is a relatively small data set, so it should be fine to just not worry about them for now and skip them when we're importing our data. So let's set this to 15, and now we shouldn't get any more errors. We can go ahead and print our data, and we'll be able to see that we have the same data, but we don't have an index column, and we don't have column headers. A simple enough validation step is to use the shape attribute of our array to show us just how much data we've actually pulled in. Here we can see we have 8,192 rows and 3 columns. In my experience, it's actually easier to work with the transpose of datasets like this, so let's go ahead and do that. To transpose a multi-dimensional array in NumPy is actually quite simple. We'll simply use the .t attribute, and now we'll see that our shape has been transposed. What transposing the dataset has accomplished is that now our 0th row is our time vector, our first is our voltage 1, and our second row is our voltage 2. So we'll go ahead and plot our first waveform with the time vector and the first row, which is our voltage 1. We'll do the same for the second vector, which is going to be our voltage 2. Now we can show, and we'll see that we have the exact same output that we were getting previously. Now let's go ahead and spruce it up the same way we did with the other plot. Let's start by adding some labels. Then let's rebase our time to get it into milliseconds, just like we did in the previous plot. And finally, let's go ahead and copy over all of the same formatting functions that we used previously. Now when we run it, we should get the same output that we got in the previous step. We can see that we have both waveforms, the output of the Schmidt trigger as well as the capacitor voltage, and we have it rebased in terms of milliseconds just for clarity. And that's pretty much it. We've found out how to plot our data from our oscilloscope in Python. Now I'm going to go ahead and copy over a little sneak peek into what we'll be doing in the next video. In the next video, we'll be using Python to calculate the actual frequency of the waveforms that we're getting. So here we can see each rising edge is indicated with the round object, and we've calculated that the actual frequency of our waveform is around 1132 Hz. So one thing to remember about Matplotlib is that it actually has a lot of tools built into it for zooming in, panning, cropping, all kinds of things that you can manipulate your data and your plot without actually writing any extra code. Now there are different applications where you would prefer to use Pandas over NumPy and vice versa. There's a lot of other applications as well where your choice of NumPy versus Pandas is really entirely up to preference. I personally use NumPy more as I find mathematics and indexing a little bit more intuitive, but a lot of people prefer Pandas because of the versatility of the data frame type, as well as the word-based indexing, which can be more intuitive for some. I would encourage you to play around with both of them. In the next video, we'll be swapping out the components in our inverting Schmidt trigger oscillator and using Python to calculate the relationship between resistance, capacitance, and the frequency of the oscillations. That's about it for this video. If you'd like to see something specific in the future, or you have any questions about the content of this video, please feel free to leave a comment. Thanks for watching.